Yesterday we talked about this new term, never heard it before, diffraction. Diffraction. The spreading out of a wave. And when we say the spreading out of a wave, we don't mean a wave changing direction. We mean just what it says, spreading out. It goes through an opening. Let's say this is my opening, and this is the wave. The wave goes through that opening. Well, you only get a little portion of that wave going through because most of the wave is going to reflect off of the barrier. But that wave that does go through, that narrow portion that does go through, spreads out around the opening. It diffracts around the opening. We used the example yesterday quite often, actually, when we open that door and I talk, people out in the hallway are going to hear me. If they're standing right outside the door, of course they're going to hear me. But if they're standing down the hallway, they're still going to hear me. And the reason they're going to hear me is because the sound wave that's coming out of my larynx or coming into my throat right now is diffracting or spreading out around the door. Now, there's three things that affect the amount of diffraction that takes place. How much it's going to spread out. Going to spread out a little bit, going to spread out a lot. The size of the opening, the frequency of the wave, and the wavelength of the wave, although these two kind of go together. You guys remember yesterday how the size of the wave, the size of the opening affects the amount of diffraction? We got two possible scenarios here, right? We got a really narrow opening, we got a really wide opening here. Which one will produce more diffraction? Which one will produce more spreading out, Tony? Good, the narrow one. The narrow one produces more diffraction. So if you got two waves here, like this, a wave incident on both openings, you're going to get diffraction taking place from both of them. A narrow portion of this wave spreads out a lot. A wide portion of this wave spreads out, but it doesn't spread out as much as the narrow portion does. So the wider the opening, the less spreading out or the less diffraction you get. What about the frequency? This is the one I told you yesterday. This is the one that I always had trouble with. Through high school and even through university, I always had trouble with remembering how the frequency affected the amount of diffraction. You guys remember that? You guys smarter than I was in high school? Louis? I'm sorry? Good. Lower frequency equals more diffraction. Now, do you just remember that, or do you have a way to remember it? Okay, good. Some of you are better at remembering things than I am, for sure. Low frequency gives you more diffraction. The way that I remember that, okay, I gave you this way yesterday, but I remember 20 years ago, I couldn't hear AM radio at the bottom of the hill. In other words, low frequency waves weren't diffracting enough to be detected by my radio in my apartment at the bottom of the hill. Whereas now I'm messing myself up. Low frequency were able to be detected. I could hear AM radio in my apartment at the bottom of the hill because low frequency waves diffracted more than high frequency waves. It's only when my radio show switched to FM radio that I couldn't hear it because those high frequency waves wouldn't diffract enough. They still diffract. When I was driving home from school, you guys talked about this yesterday, right? When I was driving home from school, I could hear the FM radio waves because they didn't need to diffract as much in order to be detected in my car across town as the AM radio waves did at the bottom of the hill. So the higher the frequency, the less diffraction. The lower the frequency, the more diffraction. Now we said 3 kind of goes with number 2 here. If low frequency causes more diffraction, then what do we know about wavelength? Well, we do know that wavelength is inversely related to frequency. So as one goes up, the other one goes down. That means if a low frequency causes more diffraction, then a blank wavelength causes more diffraction. What is it? Low or high? Going to be a high one. Good. A high wavelength causes more diffraction. In other words, the further the waves are apart, the more diffraction you're going to get, the more spreading out of the wave that you're going to get. Right? All right. Yesterday we did this crazy diagram as well. And we won't go through this entire thing again, but we'll just go through the very basics of it. We had two openings here. We call this a double slit experiment, a double opening experiment. Two openings, waves incident on both of those openings. And when the waves go through those openings, they diffract. They diffract around both of the openings. Pretty small openings, so they diffract a lot. Now, those two waves, as they diffract, will eventually hit each other. And when they hit each other, we get that phenomenon of interference taking place, either constructive or destructive, depending upon what's hitting each other. Yeah, go ahead. Yeah, were you not here yesterday? So we get constructive or we get destructive interference depending upon what place it is that we're looking at. Yesterday we said these dark lines or these thicker lines are going to represent crests, and these thinner lines are going to represent troughs. Well, when a dark line hits a dark line, when a crest hits a crest, we get constructive interference. And yesterday we drew a little red dot whenever a crest met a crest. But we also do a red dot wherever a trough met a trough, because we get constructive interference there as well. Right? Crest meets crest, get a big crest. Trough meets trough, get a big trough. We do a red dot wherever we had constructive interference, when it was crest meets crest or trough meets trough. In other words, when it was heavy line meets heavy line or light line meets light line. Now, I don't remember what color I used yesterday, but we used another color to illustrate destructive interference, where crest met trough. In other words, where heavy line met light line. This is an area of destructive interference. We start seeing patterns here after a little while. Start joining these together. What we end up seeing is these areas. If we're looking at this wave pattern from above, we end up seeing these areas of constructive and destructive interference. In other words, you're in the swimming pool, you got a guy sitting on a mattress or a girl reading a book on an air mattress just enjoying the sun in the pool. But you got these two waves that are being produced over the side of the pool from something. If that person is laying on the air mattress right here, then they're going to calmly enjoy reading that book, because there is no wave there. They've canceled each other out. The crests and the trough have canceled each other out completely. It's calm water there. It's destructive interference. But yet, right beside that area, right beside that, if the person's on the air mattress right here, they're going to bob up and down like crazy because we have constructive interference there. The crests are twice the size, and the troughs are twice the size because of this constructive interference. Right? Next year in Physics 30, this is a little bit of a heads up on something to do in Physics 30. We talk about this in the context not of water waves or of sound waves like we talked about yesterday, but we talk about it in the context of light waves. Okay? Now, in light waves, you can't actually see the areas of constructive and destructive interference in here, because light has to reflect off of something to see. So in the end, what we do next year is put a screen up here. We put a white screen. What do we end up seeing? Well, where we have constructive interference, we'd end up seeing a bright spot. And then next to it would be a dark spot, because it's destructive interference. And then next to it would be a bright spot. And then a dark spot. And then a bright spot. Wherever the antinodal lines hit, that's the lines of constructive interference hit, we get a bright spot on that screen. And wherever the nodal lines hit, we get a dark spot. Okay, we'll talk more about that next year. Good? That's pretty much where we left it yesterday in terms of notes, at least. Okay, we did go a little bit further yesterday, just in terms of a demonstration and a basic concept. Talked about standing waves. A standing wave, if you remember yesterday, was a wave that appears to be standing still. The demonstration we did yesterday, remember I sent a wave pulse down, or I sent a wave down that string at a frequency of 4 hertz. At 3 hertz, The wave went down, reflected back, and produced an interference pattern that looked almost random. But at 4 hertz, the wave went down, reflected, produced an interference pattern that was pretty unique. It looked like the wave wasn't moving. Increased it to 5 hertz. Again, the interference pattern was still formed, but it looked almost random. 6, 7 hertz, same deal, almost random interference pattern. But at 8 hertz, again, magically almost, the wave appeared to stop. The wave appeared to be standing still. Those were standing waves, waves that appear to be standing still. The waves are still traveling from one end to the other, coming back, reflecting off, interfering with each other. But they look like they're standing still. They appear to be not moving. That's why we call them standing waves. We just said they're formed by the interference of waves with other waves of the same frequency. Generally, standing waves happen when the wave you're sending down reflects and comes back and interferes. Of course, they're going to be the same frequency. But they can also occur if, let's say, we got a source of a wave over here of 10 hertz and then a source of a wave over there of 10 hertz. 2 different sources can make it work. Usually it's the same source. It's formed by the interference of 2 waves that have the same frequency, but it's a very special frequency, not just any frequency, a very special frequency. You guys remember resonance, right? It's got to be the resonant frequency. The resonant frequency of that string yesterday, there was lots of resonant frequencies of that string, actually. The first resonant frequency of that string was 4 hertz. That's the one that produced the first standing wave in the demonstration. The second one was 8 hertz. The third one was 12 hertz, and so on. And there you go. Standing waves occur only at these special frequencies, at these specific frequencies that we call the resonant frequencies. Who are my guitar players? I asked you yesterday, but I can't remember. Sometimes even when we play an instrument, I don't play any instruments, but I know my son plays piano, and he's in grade 6 this year, does tuba in grade 6. Let me tell you how excited I am about that. Okay, that's fun. Let me tell you, when he comes home with his tuba and practices in grade 6, if you could sense my sarcasm. Tuba is he's got a little work to do on his tuba. But he's a pretty good piano player, actually. But he doesn't know anything about standing waves. He doesn't understand anything about resonance. Okay, a lot of times we're very good musicians sometimes. We know nothing about resonance or standing waves. But the reality is, when we play a guitar, we pluck the guitar string, there's a whole lot of frequencies that are generated in that guitar string. But most of them disappear, like almost instantly. Most of them disappear right away. The only ones that remain are the standing waves, the resonant frequencies. If you could see that guitar string vibrating more, you magnify it, then you'd see these standing waves. Those are the sounds that you hear, the resonant frequencies of those strings. Same thing with a tuba, okay, same thing with a flute or some kind of wind instrument or brass instrument. Same thing, except it's even more difficult to see the standing waves because it's air vibrating as opposed to actual strings vibrating. This is a diagram here. Actually, I'm going to redraw that because that's not a great diagram. What I'm about to show you is a diagram of what I showed you yesterday in the demonstration. It's also a diagram that could represent a guitar string as well. The string is attached at both ends. There's lots of different standing waves that can be set up. This would be the second one. Remember yesterday we saw one bump in the middle for the first one at 4 hertz. Then at 8 hertz we saw 2 bumps. This is the 2 bump one. This is the 2 antinode standing wave, the second standing wave that could be set up, the second resonant frequency that causes standing waves. The bump in this standing wave is what we call an antinode. The antinode, where the antinode occurs, you have physical movement of the wave, although it may not look like that. Okay, yesterday I think I had, who came up and put their fingers, was it Lewis? Come and put the fingers around the two strings that looked like, sorry? Was Jacob? Okay. Jacob, it felt like the string was in two places at the same time, right? But it wasn't. It can't be in two places at the same time. This string or this wave is going back and forth, up and down like this, right? Where there's an antinode, there is physical movement, even though it doesn't look like that. Where there's a node, on the other hand, where you have complete destructive interference, there actually is no movement. Okay, the crests and the troughs have completely canceled out, and there is no movement. The antinode, where it's constructive interference, you get a big crest, you get a big trough, and they alternate several times per second, so it looks like it's just one big thing. But there is that actual movement. For the node, there's not. It's complete destructive interference, and it's that way all the time. So how many antinodes do we have here? Well, there's an antinode, there's two antinodes. Here's a node, here's a node, here's another node. There's three nodes, there's two antinodes for this particular standing wave. The part of the wave that's still, I've drawn that diagram right here, but I told you it wasn't a great diagram. It's more circular than wave-like there. Try to do it on Microsoft Word. It just didn't work out so well. The diagram that I showed you a second ago is a better picture, but this description down here works. The part of the wave that's still, it's not moving, that occurs as a result of destructive interference is what we call the node. The part of the wave that appears to be still, but really is not still. Really, it's going up and down several times per second. The one that's a result of constructive interference is an antinode. Now, what you see on the board right now is essentially four different, call it guitars, okay, four different guitars with a string in between the ends of the guitar. Okay, 1, 2, 3, 4. What I want to draw here now for each of these is a standing wave that will occur. The first diagram is going to be the first possible standing wave. The second diagram will be the second possibility, the one that occurred yesterday at 8 hertz in our demonstration, 12 hertz, 16 hertz, so on. The first standing wave that will occur will have one antinode. I'm going to draw the bottom one as a dotted line, just to remind us that the string can't actually be in both places at the same time. It's either at the top or the bottom or somewhere in between. It just looks like it's in both places at the same time. So we got one antinode in the middle, and we have two nodes, one at either end. And it's fixed. The guitar string is attached at both ends, so you have to have a node at the ends. Now the second one that would occur is going to have two antinodes. So we draw it as kind of a full wave there, and then we just draw the complement portion to it as well. It's not great, but let's try to redraw that a little bit. Okay, a little bit better. It's going to look like this. Two antinodes with three nodes. Notice there's both cases here, there's one more node than there is antinode. You can probably guess what the third one's going to be. If we had one antinode and two antinodes, we're going to have three antinodes in this one. Let's try that one again, too. There we go. That's a little bit better. 3 antinodes and 4 nodes. And then the last possibility, well, not the last possibility, we could keep going forever and ever. But the fourth possibility, the last one that we're going to draw, is going to have 4 antinodes and 5 nodes. See how sometimes it gets a little bit tricky to draw these things. That's why it's a good idea to use a pencil. Sometimes we mess up on these things. So 4 antinodes, 5 nodes. Now, the purpose of the diagrams that we just drawn, you guys saw these yesterday physically with your own eyes, so we don't need to draw the pictures so that you know what they look like. You know what they look like. The purpose of these diagrams is to help us figure out when these standing waves will occur, at what frequencies. Yesterday we did it by trial and error. Yesterday we found by trial and error that the first one occurred at 4 hertz and the second one occurred at 8 hertz and so on. Today we're going to figure out mathematically when it's going to occur. If you're designing a musical instrument, you might want to know what sound it's going to make for a particular length of guitar string or for a particular tension of guitar string. Okay? Today we're going to figure out how to do that. So here's what I want to do. I want to define in all 4 cases the length of the string as L. Okay, the length of the string is L. Whether we're talking about the first one, the second one, the third one, or the fourth one. Length of the string is L. Now what I want to do is relate the length of the string in all 4 cases to the wavelength of a wave. So I'm going to draw over here, just off to the side over here a little bit, a wave. And I'm going to draw little lines at each half of a wave. There's my axis there. There's 1 half of a wave. There's 2 halves of a wave, right? 3 halves and 4 halves of a wave. So every half of a wave, I've got a line drawn. You guys don't need to draw that. Okay, I'm just drawing that for reference when I do something over here on the left-hand diagram here. I want you to look at that first diagram right now, and I want you to tell me how much of a wave that is. I see 1 crest, right? It's going from equilibrium, crest, back to equilibrium. Take a look at this reference diagram over here and tell me how much of a wave is that? Is that a half of a wave? Is that a full wave? Is that 1.5 waves? How much is it, Lewis? It's a half a wave. So I'm going to say that L is equal to 1/2 of lambda there. Now let's take a look at the next one. The length of the string is still L, but let's relate now the length of the string to the wavelength for the second diagram. How much of a wave do you see there in that second diagram? Yep. Yes, you could, yeah. The reason I'm making it, you'll see why I'm making it 1/2 lambda in a second, but you're absolutely right. Mathematically, you could say lambda over 2. You could say 0.5 times lambda. All of that stuff would be fine. We're just going to start seeing a pattern here in a few moments here. It makes it a little bit easier to see the pattern if we have it as 1/2. That's all. It's mathematically no more correct than what you're saying. Okay, what's the next one? How much of a wave is that? How much of the wave do you see there in that second diagram? 1. It's a complete wave, right? We're going from here, okay, all the way to here. Okay, that's like saying this. That's a complete wave. We could say it's 2/2 waves, or we can just say 2/2 times the wavelength, or we can just say it's lambda. You know what? Let's make it 2/2. Let's call it 2/2. Even though in the end it's the exact same thing as just saying lambda. Now, Lewis, you could say, by the question you just asked a minute ago, couldn't we say lambda over 2 for the first one? Yeah, that would simplify it a little bit, right? Okay, saying L is equal to lambda would simplify this a lot, right? But we're saying 2/2 just so that we can see a pattern in a few minutes. Yeah, you could say 2 lambda over 2 as well. Yep. Yep, exactly the same thing. What about this one? This one we're going from, let's trace it out on our reference diagram over here. Okay? Looks like that, right? What do we got there? Well, that's 3/2. So L is equal to 3/2 of lambda. And the next one, well, if we keep going one more half of a wave, we've got 4/2 of lambda. So we start seeing a pattern there, right? The length is progressively, it's going up by a factor of 1/2 lambda every time. Now, here's the real big step. It's not necessarily the hard step. What we've just done, I think, is the hardest step. But it's kind of the crux of what we're doing here. We're going to say, actually, let's do one more thing first. Let's rearrange this to solve for lambda. Take the 2 up by multiplying, it becomes 2 times L. Well, this is just 2 over 2 times L. Lambda becomes, the 2 goes up, the 3 goes down, it becomes 2/3 times L. The 2 goes up, the 4 comes down, it becomes 2 over 4 times L. So we're just rearranging it to solve for lambda, that's all. And now comes the crux of it, where we're going to say V is equal to F times lambda, and rearrange that to solve for F. F is equal to V over lambda. Well, lambda is 2L. So the first standing wave on this guitar, or whatever instrument it is going to occur at a frequency that's equal to the speed of the wave divided by 2 times the length of the string. Now, we could change that frequency by changing the speed of the wave, right? Or by changing the length of the string. Guitar players, there's 2 ways to change the pitch of your string. What's one of them? Tuning it. Okay? If you turn that little tuning knob, you change the pitch of the sound, right? You do that because when you change the tension in the string, you're changing the speed of the wave. If V changes, then frequency changes. You hear a different sound, right? If you tighten it, the wave goes faster and the sound gets higher. That's the other way. What's the other way to change the pitch of a string? Put your finger on a fret. What are you doing when you're putting your finger on a fret? Go ahead. You're shortening the string. If L gets smaller, right? If L gets smaller here, then F gets bigger. When you put your finger on a fret, you shorten the string, you increase the frequency of the first standing wave that's produced in that string. Now let's take a look at the second one. Once again, F is equal to V over lambda. But lambda is 2 over 2 times L. Let's just make it F is equal to 2V over 2L. You could simplify that if you want, Lewis. It goes back to your question a few minutes ago. F is equal to V over 2L would be the exact same thing. But here we start seeing the pattern, right? V over 2L. 2V over 2L. Next one, we get V over 2/3 L. Now we can simplify that a little bit by saying 3V over 2L. You guys know the math there? Or does this seem kind of foreign to you right now? If I go V over 2/3 L, that's the same thing as saying V times 3 over 2 times L, over L, I should say. When you divide by 2/3, it's the same thing as multiplying by 3/2. That's why V over 2/3 L is the same thing as saying 3V over 2L. And the fourth one here, F is equal to V over lambda, which is 2/4 L. V over 2/4 is the same as 4 over 2. So what do we see here? What's the pattern that we see with these frequencies? The first standing wave that's set up in the guitar string, or whatever other string that we're plucking, is V over 2L. The speed of the wave divided by 2 times the length of the string. The second one is 2v over 2L, 3v over 2L, and 4v over 2L. This one we're going to call the first harmonic. This one we're going to call the second harmonic. The second harmonic is, by definition, twice the value of the first harmonic. And the third harmonic is 3 times the value, right? 3v over 2L, not v over 2L. It's the third harmonic because it's 3 times the first harmonic. And the last one is, of course, the fourth harmonic. There would be a fifth and a sixth and a seventh as well, but I don't think we need to go any further to understand what's happening here. Yep. Yes. Yes. The first harmonic is also called the fundamental frequency. And then the second harmonic, you could also name that the first overtone. So yeah, I'm not going to write those down because we don't actually have to know that. But first harmonic, fundamental. Second harmonic, first overtone, because it's the first tone that's over the fundamental. Third harmonic would be the second overtone. Fourth harmonic would be the third overtone, and so on. Kind of make sense? Kind of? A couple of years ago, I was painting in my house, and the entry area where the doorbell is, like not the the button for the doorbell, that's outside, of course, but the ding dong part of the doorbell is in that entry area of my house, and it's got a little box over the doorbell, just to make it look a little nicer or whatever. Well, when I was painting, I took that box off because I didn't want to get paint on the box on the doorbell, right? If I got paint on the inside of the doorbell, who cares? I don't want to get paint on the outside of the doorbell because I didn't want it to look bad, right? So I took that box off. And when I took that box off, I looked at the doorbell and I thought, this is ingenious. Like, how simple is this, how this works? But it never occurred to me before how a doorbell actually worked until I took the cover off and saw it. There is, in one of the, not one of the electronic doorbells, but one of the ding-dong doorbells, which most of us have, I think, there are 2 steel rods in that doorbell inside. 2 steel rods. The top one is short. The bottom one is long. There is a hammer that will be forced to go up electrically. I won't go through the electromagnetic portion of it. That would be a physics 30 thing, but could do it in physics 30, but don't need to know about that here right now. There is a hammer that when you press the doorbell goes up. And then when you let the doorbell go down, when you let go of the doorbell, it falls down. So when you press the doorbell button, this goes up. When you let go of the doorbell, this falls down and hits the bottom one. When it goes up and hits the top one, it goes ding. When it falls down and hits the bottom one, it goes dong. Why ding and then dong? Because this one's shorter. And if you look at the equation, F is equal to V over 2L, for the standing waves that are set up inside those 2 pieces of steel, the shorter the length is, the smaller L is, the bigger F is. So this one, when it's struck by this hammer, is going to produce a higher frequency. This one, when it's struck by the hammer, is going to make a lower frequency. Hence, ding, dong, high frequency, top one, low frequency, bottom one. It's as simple as that. Okay? Standing waves, set up not in a guitar string, this time set up in 2 pieces of steel inside my doorbell. How many of you have a doorbell that's the ding-dong doorbell? Some of them are electronic, crazy ones now. Okay. Go home tonight, and when... So here's an example of a question involving standing waves, involving these strings. Unfortunately, it's not in your books. You're going to have to copy it out. It says a 25 centimeter long string is set in vibration. Now, this could be on a guitar. It could be on a ukulele or some kind of a harp or some kind of other stringed instrument. Even a piano, which is really just strings, right? The speed of the wave through the string is 500 meters per second. What's the first three possibilities for harmonics in the strings? In other words, what are the sounds that we hear from that string? What are the resonant frequencies or the standing waves or the harmonics or the sounds that we hear? Well, there's a couple ways we can tackle this. The first way, and just hold off on writing this down yet, okay? Just wait till you see what I'm doing here, and then you can write. The first way is to draw the first three harmonics. There's the first one. Okay, the second one, remember, had two antinodes. And the third one had three antinodes. So you can do that. That's absolutely fine. And then after you've drawn those first three harmonics, you can derive the equations that go for each of them, just like we did right here. Calculate the frequency of the first three harmonics by using V over 2L, 2V over 2L, 3V over 2L, having derived the equations just like we did right here. But there is an easier way to do it. We can draw the first diagram. We can derive the equation for it. Okay, this is L, the length of the string. We know that L is equal to 1/2 lambda, and therefore lambda is equal to 2 times L. We know that F is equal to V over lambda, or F is equal to V over 2 times L. We can calculate the frequency of the first harmonic here by saying 500 meters per second divided by 2 times the length being in meters, 0.25 meters. 500 divided by 0.5 gives me 1,000 hertz. There's the first. I can do, again, the same thing for the second and the third, derive the equation just like I did in the first, just like I did in the diagrams over here, or I can remember the pattern. The second harmonic is twice the first. The third harmonic is 3 times the first. So if I want to find out the first harmonic, I've got to do it like I just did it. But if I want to find the second harmonic, it's simply going to be twice the first. If I want to find the third harmonic, I remember the pattern. It's simply 3 times the first harmonic. So, if you remember that, that's great. Now, there is some value in being able to derive the equations for the second and third and do it that way, the way that we did it right here. If I derive the equations for all three of these, and I get the same values as I got here, 1,000, 2,000, 3,000, then I must have done it right. So it's a little check. Deriving the equations for the second and third can be a little check, but it's not necessary. If you can derive the first one and then remember that the second one is twice the first one, that's good enough. So what happens here when I pluck this guitar string? There ends up being 2 or 3 or 4 different harmonics that are set up. There ends up being a combination of sounds that end up hearing from that string. Combinations of 1,000, 2,000, 3,000, so on. Handing around a worksheet right now, a little booklet of worksheets actually. I want you to do, there's 4 pages to it. I want you to do the first 2 pages up to number 8. I think there's 11 questions on the first 2 pages, and I want you to do the last 3. Do the first 8 questions on the first 2 pages. They all relate to this, okay? And again, you got a couple of options for most of these questions. Derive the equation for the third harmonic or the fifth harmonic or whatever harmonic it is that you're asking you to solve for, or just do the first and multiply it by 3 or 5 or whatever the case may be.